reminding me to start the recording. Yeah, yeah. So before we start, so here is the first thing that I want to show you, right? Okay. So you see this, right? This is what? It's a dark image. Okay, it's a dark background on some huge circles drawn in colors, right? And some small circles too. Right? You must be wondering what this is, and it's like just a small image. What significance does it have? Right? So to tell you, this is a map of the current internet today, right? Uh, so this one diagram has about around 300 million nodes, okay, and we are not able to see everyone because the size of the node is based on the number of visits to that particular node, right? So most of the things that you see here, like the big ones in the middle and these things, this is probably the Google node, and this is probably the Yahoo node, and so on. That this is like the entire map of the internet, which is a currently ongoing survey which is run on the internetmap.org. You can go check it out later. It is a cool interactive website. Okay, I'll leave you a link to that. Connect. So you can go have a look at it when you after the class. So cool interactive website, okay, which maps down and tells you in detail about all the websites on the internet. So we'll start off with a network that is not so huge, not so big, because this is such a clumsy network. So we'll start off with something small, and we'll eventually go up to here. All right. So the first question, before all of the internet and intranet and all of the things that we want to talk about, there's something called as a sneaker net. Have you guys heard of it before? Let me just give you a quick poll. Have you heard of the sneaker net? No? I see almost all of the people. Oh, I see two S's. I am wondering, Akash Jain and Tamlio, one. So you said yes. Do you want to tell us what that is? What is the sneaker net? Yeah, you can speak, both of you, if you're up for it. Or you can put it in the chat too. What do you think? No? So is that a yes by mistake, I guess? Okay, let me just tell you what a sneaker net is. Okay, so remember the time when computers were, or computers or any kind of a computing device was not a small thing? In the 1950s and 1960s, right, when the computers eventually came into from ideation to existence, when you had big machines, right? And I am sure that all of you know that they were. So one of the first computers was the size of a city block, right? So and eventually they did shrink down to sizes, and universities and campuses and companies could start building their own computers. And the thing was, all of their computers that they used on campus, say on a company campus, was say on a building A to a building B, uh, were huge distances. Anyways, in the US, it was very large campuses, and computers usually used one from one computing department to another computing department. There were huge lengths, so people, if they wanted to share data between each other, right? So if one computer runs one problem and the next set of it had to be run on the computer B. What people had to do was they had to take the punch cards. So punch cards were the things that you were initially using for programming back in those days. Or they also had, in more advanced versions, you had the magnetic tapes, right? Which is still a thing. Magnetic tapes still a thing, but back then they held very small amount of data, but right now they hold up to say 330 terabytes of data on like such a small device, right? So magnetic tapes were so people had to carry, from yeah, CMDO is yes, transforming data physically, yes. So moving data using those magnetic tapes or punch cards, people used to carry them around from one place to another, and that was how data was shared back then, right? So, and that was not just the only problem. You had something like a common printer in your office, like in 1980s, and you couldn't just connect. You couldn't have a printer for every computer, right? You had to make sure that there was one printer and all of the computers in the campus had to, or in the room had to share it, or any other such devices on the internet which could be shared, right? So this was eventually leading up to the cause of, you know uh, towards networking or sharing data between computers. So this comes give rise to our first stop, which is the local area network, right? So a local area network is, say, two computers. Just say it can be as small as two computers that are connected to each other. Okay, maybe say like an Ethernet wire, right, which is a copper wire, or like in Wi-Fi, or it can be as big as a university, and where there are thousands of computers that are connected simultaneously. Okay? So what local area networks enabled us to do, looking back then, is to have a have sharing of data through wired connections. All right, wireless is a very new thing. All we had back then was wired connections, and so we could share the data that were computed at one place to another computer that is located in somewhere else entire, right, on the same campus. So there are different types of technologies when it comes to LAN sharing, like data sharing among LAN technologies. That is, say, like wireless fidelities, the Wi-Fi or the Bluetooth. Okay, but one of the thing that is common that you see all over the place, which is still in use, is the Ethernet. Right? So Ethernet was first conceived at Xerox PARC. Okay, it was somewhere in the 1970s. Okay, and it was conceived by Bob, uh, and this is one of the first his diagram of how the Ethernet works. And back then, you didn't have to even you know he conceived it for, say, telephone lines and how they would work, and say, let me just, okay, take out the annotation tool so that you can follow me too, right? So Ethernet is basically a common, is like just connecting computers, right? All of your computers through a common grid, right? See, remember, to give you an analog of how Ethernet works, is like that how your homes share electricity, right? So what you have is an electrical transformer, and the transformer gives you lines, and every line is connected to your home, right? And the same way, every computer on an Ethernet is connected to each other via a common line, right? So let's just have a deeper delve on looking into how Ethernet works, and remember, Wi-Fi also works in a similar way. So whatever we are going to be talking about the Ethernet, all right, is going to apply also for Wi-Fi, right? So both the Ethernet and the Wi-Fi work in a way. How they work is they do work by broadcasting messages on the common shared uh, media, right? So what happens is that, see, you have say say two computers or three computers connected to each other via an Ethernet. So it is just like connecting them via copper cables, right? Ethernet is nothing but copper cables running throughout. So all three of them are connected to each other via the Ethernet, and say computer A has to send a message to a computer B, right? What it does is it broadcasts the message on the common sharing line, right? Now let me show you with an image. Oh, yeah, this is more of the one. Okay, I've not included that image. So yeah, so what it does is, say you have, say, what, say computer A, computer B, and computer C that are connected with a common internet Ethernet line, right? You're able to see this. A and a B and a C. All right. So what happens is that, say if A wants to send a message to C, right? So what it does, it sends a broadcast message over this copper line, which is going to be a signal, an electrical current carrying the message, right? And what happens is, when it broadcasts, both B and C receive the message simultaneously, right? But how do you know who's for whom is the message for? Like, is it for C or is it for B? To solve this, what people made was to design a structure, address for each computer, which is called your MAC address, right? A MAC address, or a media access control address, is a physical address of your Ethernet devices or your Wi-Fi devices. Okay, so if you just pop open your terminals, okay, you can just type in fconfig -a. I put it in the chat, right? You can just type it in and have a look. Okay, so there'll be you can try it out in both on your term UX and on your laptops as well. So what that would give return to you would be a list, okay, a list of, which has a lot of different things, and you can look at, say, some Ethernet ETHO or Wi-Fi O or WLAN O, and it will have something called as an hardware address, HW address. And that HW address, or sometimes even it will be written as a MAC address, is actually the physical address of your device, okay, your hardware. The Ethernet, the one that converts your electrical signals, is called the Ethernet board. And that has a physical address etched onto it physically. And the same way for the Wi-Fi card, right? It has a physical device, and it is going to be a permanent address, so that when you're connecting to in a local area network, right? Like when you're connecting to your Wi-Fi, right? So your Wi-Fi routers, they know which device is yours and where to send your packets, or the messages on that need to reach to you, right? So so this method, all right, or this approach of sending messages on a common shared platform, right, is called as a carrier sends multiple access. carrier sense multiple access for short, or CSMA for short, which means you are sending a message over a common shared carrier medium, like say a copper, like the Ethernet cables in your Ethernet case, or radio waves in your Wi-Fi, right? So which is carrying you the data to your computer, and this helps you identify which device the message is sent for. All right, and you can look it up and decode the message. Like IP address for the internet, Mahesh, yes, we'll get into that much more deeper, how IP address comes to the internet. Mhm. How IP actually comes into the picture, right? We'll get to that, Mahesh. Okay. So yeah, also you can ask questions, you can stop by, interrupt me, ask me doubts if you find anything, or if you find something is wrong over there and something that I'm saying, you can just stop me ahead and tell me, okay, this is this, right? Okay, now there's a problem when you are using a shared medium, right? So see, if somebody is connected to yeah, I guess if one of you can just say Prithvi or Shashank can unmute yourself, right? One of you can just go ahead and do that. Somebody unmute for me and speak up. Yeah,
Uh,
Shashank. So you know, just try to speak simultaneously with me.
okay, I'll try that.
Okay, let's just try to read out the first sentence, all right? Which is, yeah, with the shared. All right, let's start on one, two, three, go.
With the
With
shared
a shared common, yeah, go
common
on.
with the
Transmission
shared
medium,
common
a new
transmission medium, a
problem
new
arises.
problem arises.
Okay, let's speak. Uh, that was good, Shashank. But how many of you actually got that? I'm not sure that if everybody got that, but since we are seeing the text, our brain just processes that and say, okay, this is the statement that they read off, right? But what happened right now is that me and Shashank, when we were reading continuously, the audio line that you are listening to gets scrambled up, and both of us are speaking at the same time, and our messages, even though are reaching to you, they are buzzed off, and it's hard to recognize what the message actually is, right? And this is just us speaking in the audio line. Now imagine in an electrical signal which is carrying a signal. What happens? Oh, you are sending two signals at the same time, and that signals, if some of you are from your electrical science backgrounds, you would know that, or if you are taking physics, if you remember the physics that you had in 12th, you remember that your signals get mixed, they add up in amplitude, or they take off in amplitude, or something happens, and your signal, which is carrying a message, gets destroyed, right? So this is a problem when you are what using a shared medium. You kind of, when say in the previous problem we had three computers, right? So now if A and C was sending a message to, say, if A was sending to C and C was sending to B at the same time, um, if they are trying to send it at the same time, their signals would intersect, and there will be a collision of the message, right? And the messages are going to collide, and none of them are going to receive the message that was intended. So a common protocol that was introduced to make sure that devices, you know, don't collide messages is the way by making sure that every computer, listens to the shared media. Like they listen to the Ethernet ports or via Wi-Fi ports continuously, and only transmit messages when the line is clear, or there is nobody else, there is no other computer that is being transmitting the message on the same media. All right. So what happens if, say, a computer, no, in our previous example, A wanted to send a message to C and C wanted to send a message to D. Now, let's say A starts transmitting, and at the same time, C is starting to transmit. Right now, C recognizes that A is transmitting a message. So what it does is it waits for A to complete its message. So by default, what happens is that uh, a time of 1 second is added as a wait time for every computer to send the message. All right, for the communication. Uh, Once it listens and finds out that another computer is alpha. But that again gives you some kind of a problem, right? Because say if you just have 1 second gap, right? Just 1 second gap. Say at the same time, B's also wants to send another message, and at the end of 1 second wait, both B and C are going to transmit simultaneously, right? And that again is going to lead to another collision. So what happens is that by default protocol, it is not just 1 second that is added to a wait time for transmission of a message, but 1 second plus a random amount of time, like say 1.5 seconds or 1.3 seconds. So zero point 0.3 seconds is added or a zero point 0.5 seconds is added. So now when C finds that it is transmitting, waits for say 1.3 seconds and sees that line is clear and starts transmitting. And when B wakes up after 1.5 seconds, it sees that C is still transmitting. So let me go back to sleep, okay, and transmit my message when C is done or there is no other traffic. So this is how the computers send messages to each other along a time. But this leads to something like, say, if it's just a 1 second gap, it is going to start pushing a lot of congestion, right? A lot of messages are going to get queued up, okay, meaning say once a line is clear and once a computer wakes up to find a line is clear, it is going to start transmitting. That is what it is programmed to do. So to avoid that, what we do is we try to have an exponential back off, okay, of sending the messages. All right. See, now B finds out after waiting for the first time of 1.5 seconds, wakes up again and finds C is still transmitting. What it would do is it would not wait for 1 second plus random time, but it would wait for 2 seconds plus some random time, right? And again, if it finds it again, it is going to move it for 4 seconds, and it is going to schedule it for 8 seconds and 16 seconds and so on and so forth. Now this helps up queuing, making sure the line is clear for messages to be transfer sent very faster. Okay, now we are just looking at an example of 3 computers, right? So this does not, for 3 computers, I know it is going to be clear and we are going to do. But when you have say 1,000 computers in your university, right? uh, I was in a university which had more so about 6,000 students and more than 5,000 to 6,000 devices connected in the university. Right? So in that case, it's going to be difficult, keeping track of the messages, and so exponential backup helps us, get those reduction on. All right. So, but it does not completely free up the traffic of messages that are on the shared Ethernet or the shared connection media. Right. So this comes up. This leads us to a next, roadblock that we are going to be solving. Right. So so now we get an understanding that for say thousands of computers, we can't have a single line that it connects all the thousands of computers together. Now that is just going to have a huge queue of messages that are not going to be sent for a very long time, right? And that is something that you don't want to happen, because you want to go for dinner and you ask your friend who's in another hostel, let's go for dinner on the internet, send a message. You want to make sure that he receives the message before the dinner time is over in your hostel, right? So to make sure that the messages or the lines are much more clearer, right? Okay. What we have, we break down, all right, the domain, all right, what we call as a collision domain. Okay? So in the previous example that we were seeing, say, well, this had actually one collision domain, right, where it had only one place, a common shared place where you could share all the messages together. All the computers could share the messages together. Uh, when we introduce a method of a switch, all right, a switch is nothing but breaking a collision domain, right? We had one collision domain. Say if we have 5 computers or 6 computers on the same thing, right? Let's just go back and I'll show you how it works. Say now we have 3 more computers, all right, that are connected to each other, and we also want to connect to the the old computers too, right? Now what we can do is we can just draw a line, but now all the first three are going to be continuously communicating to each other, and the new three also are going to be communicating, right? And this is remember, now that's if you are going to start adding more and more and more and more and subclusters like that, it is going to get uh, the whole line is going to get clocked very quickly. Now the switch helps us resolve this. Okay, so between the set, say this is your set one and this is your set two, if you introduce a switch, all right, okay, switch is going to help us manage the amount of traffic, okay, the amount of messages that are being sent on the network, all right, by uh, making sure the network is being split, or we are having two collision domains. Okay, so here you have one collision domain and you have another collision domain, right? So what happens is that now say if A wants to send a message to C, okay, if without the switch, it would flood the entire network with the signal. Now with the switch, uh, the A can send a message to C without flooding the whole network, and this is done uh, by that way that the switch knows what MAC addresses, or it contains a record of addresses of which computers are on which side of the network, right? So it knows, say this is D, E, and F, okay, are on this side, and A, B, C are on this side. Now here, A can send a message to C without flooding the whole domain, and say if say computer D wants to send a message F, it will only flood this network and it won't go over to this spill over to this network. But when say A wants to send a message to E, the switch activates and the whole network is flooded, and you have a message that is being transferred from A to E, and E recognizes that this. Oh, I did forget to mention. So how is these messages are being identified, by each computer, right? They are identified by giving a MAC address, right? So now each message, okay, is added a MAC address in its header, okay, so that once you receive a message, that is the first thing that you're going to read, and each computer knows that the MAC address. Each computer knows its MAC address and it receives its own, uh, and it knows its message is intended for it and not the others. So yeah, so switch is so basically the whole internet, is connected. The whole internet is not just thousands of devices, it's billions of devices. And we are reaching a bottleneck of, say, 10 billion devices, okay, right now, that are connected to each other whole, all over the world. And without switches, okay, meaning switches, if you didn't have switches, you and had only one single whole connection to the whole world, just imagine how miserable our lives are going to be, because nobody is going to get our messages. And the the whole way that switches helps us build, smaller and smaller and smaller networks which can get interconnected to form what we call as the internet, the whole thing, right? Okay. So now with that, we get to a crucial part of, right, how messages are being sent over the internet in general, right? So let's just move on from the local area network on to the broader spectrum of, internet. So now we understand that, see, the messages in a local area network are going to be sent with a common shared media, right? And they are going to have a packet of message which with the address, with a MAC address, right? A MAC address as its header, and a computer, all the computers receive the message and only parse the message that has its own MAC address. Um, but say if you want to transmit from your local area network to somebody else on, say, on a different state. For example, we are in Bangalore right now, and you want to send a message, yeah, signal of message to your friend who's probably studying in Kolkata, right? So this so connecting all your look. So now usually how we can do is, we can have a dedicated line for you, and say right now we are connected in Bangalore, and we can have a direct line to Kolkata, okay. um, and that direct line to Kolkata would activate once you want to, say, send a message to a person in Kolkata, and you can have your own, mm, you know platform, right? So you can send your messages to your friend in Kolkata by using that connection. But that is a single connection. Say in physical terms, it's going to be something like a whole cable that is going to be connected from Bangalore to Kolkata, right? Okay. So that is going to take a very huge terms in the cost of infrastructure, because you are just having one single line that is going to get carried from Bangalore to Kolkata. But instead, the internet, our infrastructure that we currently have is much more better, right? It's much more intelligent. So you don't need to have a single straight line to Kolkata to communicate, send a message from Bangalore to there. So what we have are, there are local clusters that are connected to everywhere. So right now, for example, we have connections. See, right now we have satellite connections. Just imagine back then, right? If you just had copper line and not any wireless transmissions. So you can connect to different cities, like, say, say here in this example you have Peter and Ralph. All right, you can just use, say, our names instead of those names. So say Harivatsa and Shashank are connected. They want to send. They are at two different localities, and they want to send messages to each other. Right. So what happens is that, so they don't, say, let's take a physical case and not something like, on the internet. So now Harivatsa does not meet Shashank every day. So what he does is that he meets, say, Apurva, right? Uh, every day, and Apurva meets Shashank every day, right? Because, say, they meet, Apurva meets him at the college, or and they, Apurva and Shashank, live near. So now, Harivatsa writes a letter, writes the address. This letter is for Shashank, and gives it to Apurva. And Apurva then sees this letter as for Shashank and passes on it to Shashank when they meet later in the day. Right? Um, so this way of sharing messages is called message switching, right? It's called message switching. So what happens is that you are sending a message on the network, right? So now you are sending a message to people, a people network, right? And you're transmitting letters through one single path. But the best part of message switching is that you can have different paths, okay, that you can take, okay, to make sure Shashank gets the message, okay. Say if one day Apurva is sick and she's not able to come to the college, right? That essentially breaks the loop, right? If that was the only connection that we had, right? Um, no, multiplexer, no, not necessarily. You're just a say this can be just not a multiplexer, but say a network router. Okay, so we can have an example of it might be something like a postal office. Okay, so something like that. Yes. So yeah, so it's just a carrier medium, right? Not just a multiplexer. A multiplexer is much more. It does a different work altogether. So if Apurva is not there, for example, on this day here, and she's not there, and what what you can do is say there's another person that Harivatsa meets daily and Shashank meets daily, who have a common friend who meet them daily, right? So he can send a message to send a letter to this guy, and this guy later passes it on to this guy, and he sends it to this guy, and finally Shashank gets the letter at the end of the day, right? So instead of just relying on one line, a network, right, of different peoples can make sure that you are able to send the message to Shashank robustly without any kind of loss in time or anything. And this is actually something crucial that you ought to remember, because say if you are just sending one a file and this line is clogged, okay, and you want to send another message, you can send it because this line is occupied, right? You can send via this line. Now just think in terms of now you can just think in terms of these nodes not just being people, but say networks, network servers, the backbones which are transmitting medias, your ISP providers, right? They are sending your holding on to your messages, and say one line is busy, you can you know send it up to the another line, right? So now the amount of hop, okay, so now here you see the message is hopping twice, right? So first it is being sent to, then being sent to another person, say person A, person B, and person C, and it takes a total of 1, 2, 3, and 4 hops to eventually reach Shashank. So this is what is called as an hop count, and this is very essential in our internet infrastructure today, because we have to make sure we keep account of how many hops a message is taking, right? So now, say what happens if say these two person, okay, if by mistake this guy C, okay, you know, thinks guy D is the best guy to give the letter instead of me going, is the shortest or the best route to give the letter than him going and giving it to Shashank himself. Uh, he sends it to D, and D thinks, okay, the best way is to send it back to C, and the messages just hop between C and D because they think each other are the shortest or the best way to send the message to Shashank, right? So when that happens, you are going to have a lot of hop counts that are going to start happening, right? And by counting how many hops it takes, you can identify if the message is actually getting lost somewhere. Okay, it is some kind of an error is in the network, or so there's some kind of a problem in the network, and you can make sure and you can go rectify and then back and send it down to Shashank all the way. So in every message that is sent over the internet, holds this count of hop count, like how many hops it is going to take for you to receive a particular message, right? So yeah, so that is usually how you solve problems of messages being logged on the network. But remember, say for example, you want to send a message, right? You want to send an email, uh and your email has an attachment of, say, a file, 25 MB, you know, textbook that you want to send your friend, right? And now that is going to be a huge load on the network, right? Because you want to occupy a single line. You are sending a message contains an email with an email attachment of a textbook, and you want to send it to your friend. Now sending this big, it's a big file. 25 MB is a big file, but now it is not, but usually it was a big file back then too. So what happens is that you you have to open a line, connect to the person, and start sending the message, and start sending the whole message of 25 MB is going to take some time, and you're going to be clogging up that line, right? That line of message indefinitely until you stop. You finish up with by sending that email attachment, right? But say if someone else wanted to send somebody else on the internet and is using the same line to send a smaller file, right? They just wanted to send a small message saying, "Hey," right? And when you are looking at that problem, and uh, you know one you have such a big file that you want to send, and you're clogging up the internet lines, it is better to chop up that big message that you want to send, chop up that big message that you want to send, and you want to make sure that the message that you're sending reaches the person but not clogs up the whole of the internet. So this is by dividing your entire message, all right, whatever you want to send in your email, and your whole file, the email attachment, is split up into small things which are called packets, right? And um, so that the big transmissions of bigger files get chopped up into small messages, and they're sent seamlessly on the internet, so that you are able to receive the message without clogging up any other people's lines, and everybody are uh, are able to get it, and everybody is able to use the network easily, right? So the same way how we use the message switching, all right, we're going to be uh, in message switching. What we did was we wrote the address to Shashank, and Shashank lives in such and such place, set it over. Here on the internet or in the network that we are using, each packet of data that we send of a message that we have chopped up has a source address and a destination address. All right. So it tells where the source is from, who sent it, and tells it who is the destination, who wants to, like, for example, Harivatsa wants to send Shashank, so he's sending a big file, and the big file gets divided into small packets, and each packet has the address of Harivatsa and Shashank, so that all the packets go to Shashank and knows where it is coming from. So so now, the format of sending, having the message split up and the packet, and each packet having in a header. The header is going to have the address of the person that you want to send to, like say for example Shashank's address. And this format was actually defined as defined by the IP or the internet protocol, right? And every address, okay, that the packets have are called the IP address, right? The same way your MAC addresses, like Mahesh pointed it out earlier, the same way MAC addresses are for local area networks, IP addresses are for the larger, wider area networks, or the internet, and so on. So so packets, instead of sending messages in blank, packet switching, helps you down to, balance out the loads and on your network, and send it via different multiple routes. So back in our example here, if you wanted to send a huge file, you could send it from here. You could split up, say, the packets. Say you are sending it in 3 packets, okay, and to Shashank, right? So you're gonna send one packet to this line, send another packet to this line, and send another packet to this line, and all of these, reach here, and it is all of them are going to have an destination address of uh, Shashank, and they're going to reach him. And but yeah, they're going to reach him a bit out of order. Like this, say if this was packet 1 and this was packet 2 and this was packet 3. Now say we divided it into 3 packets of our whole messages. Now see, you can see by just the hop counts, see this has 1, 2, 3 hops, this has 2 hops, and this has 1, 2, 3 and 4 hops. So you are going to have a message of order, say one first packet and third packet and third second. Now we'll also look at how this problem is solved by a different protocol that lies on top of your IP protocol, right? Internet protocol. Sorry. So, so getting back. So yeah. So this way, once you're splitting up all of your packets, you are also balancing the load on the network. Now, once you don't have to queue it in the same line, you can split it up, and all of it are sent at a very faster rate, and the congestion or the traffic on the network gets very less, and you can have seamless communication going through. So just before we jump on to the next section, which is going to be talking about our IP protocols, I just wanted to show you this. This was a diagram of the ARPANET, and for I'm sure all of you remember the ARPANET, right? It was uh, built by the it was funded and it was built in America, and not just America. If you can just see, let me just so I can see too. So you can see here all of these nodes are some computers that are connected or devices that are connected, right? And these are locations, say Utah, Illinois, and even you're connected to the London via a satellite connection. So ARPANET was one of the first, versions of your internet. So it is something you could say that kickstarted the era of our internet communication, and it was mostly funded during the Cold War and World War II and Cold War times. It was probably in the Cold War times, not the World War II times. So So this was actually built so that if you just had one communication line that ran through, say, one point to another, say from Utah to some place over here, and you just had one line, it was easier to destroy that line just by destroying some kind of a transmitter. But you had a robust network like this, a message could take different paths to reach its destination, right? So that destroying just one trans receiver or one transmitter would not uh, would not matter, because the message would eventually get transmitted to the destination. So yeah, so jumping back to what we were discussing, the internet protocol. Right now, the protocol that we use is what is called as the internet protocol version 4, right? So every packet that is sent on the internet via the internet protocol version 4 has these kind of things that go into your you know in your packet, right? It is going to have the data, say for example in your email, you're going to have some file or some email that you are going to transmit, and that is going to be stored here. But that is not the only thing that you need to transfer, but you have to make sure that you specify whom you are sending to, your destination address, okay? And it also has a source address, okay, which is going to tell you where the um, message originated from, to make to hold on to that. And it has in its metadata, it has something like your total length and your header checksums. So, and your protocol, whether a protocol is like a TCP or IP or a UDP or ICMP. So there are different protocols within IP protocols that would help you send the messages, and that we'll look at how that works in a short while. So, and it also has something called like a checksum, right? So, say for example, your data had, say, some 4 digits. Okay, so 11. Okay, 4 blocks. Okay, and okay, let me just delete that. That's bad. So you had so 4 column, 4 things to transmit. Okay, and each thing had, say, select this, a number. Okay, so this has 11, this has 12, this has 04, and this has 20. So your checksum is going to be just the sum of the whole data that you're transmitting. All right, so it is just going to be a sum, and here our sum is 24, 36, and 47, right? And this is going to go into the header checksum. And why is this checksum important is because, say now you're transmitting through a grid, right? You're transmitting a message from, say, Harivatsa to Shashank via different paths. And say if there is some kind of a corruption or some kind of a signal error, or there's something goes wrong and your message gets corrupted, these numbers are going to change, right? Say what you sent was 04, but what you received was 03, right? 03. And that actually changes checksum, right? And once the checksum is changed, okay, checksum is already computed, and our original checksum is, say, 47, right? 47. Okay, and your checksum is reduced by 1 digit, you know that the packet that is containing the data has been corrupted while taking a path, and you have a packet loss, right? So how computers usually handle that is by discarding this packet, and they don't use this packet. But there are you know places where your packets have importance to, and we look at how to handle those issues in the next video, right? So basically, these are some of the things that we'd want to, I want to talk to you about your IPv4. So to just recap your IPv4, it has a header, okay, and your data, okay. The header contains various information of the source addresses and destination addresses. It has data of whether the data that you're sending is correct via the checksum, and you have what protocol the message is being sent to, right? And we'll be looking out at the protocols of how things look at. And the first one that we'll be looking at is what is called as a UDP, right? So, for example, right now we are having a video call over the internet, and this video call is being sent to you, okay, via lots of packets. So now this audio that you're listening to is being broken down into small packets and is being transmitted to you. The video that I'm sharing via my webcam is being distributed into a packet and is being shared to you. And the same way, what the slides and the movements of my cursor is also being shared to you, right? And it is a huge transmission that is happening from me to you. So usually applications require, okay, separate applications like the browser right now that we are using need to make sure what it is listening to and where to get the data from. For example, our browser is currently using the port, say 80, all right, because this is a HTML5 supported video conference, okay. It is using the source port of 80, but say something like Skype, which is a standalone application, which you don't need a browser to launch it, and you can launch Skype itself, would require port, say something like 3000, okay, to run into. And why this is needed is because, see, they need to have a continuous stream of data, right? Because your videos, or say here in the case of Skype, in your Skype video calls, you need to have a continuous data that is being transmitted from the source to your destination, right? From me to you guys. What eventually would happen would be that you need to have establish a separate connection on a different port and make sure the other ports are free for other communications, and this port is only used for the video call. Right? So this way, what you do is you have, by opening it in a port, you can listen to that, okay, and I can send you data through that port, and you can listen on to that port and make sure all of that. And here, uh, that's what UDP actually does. So you have a source port, which I'm sourcing you from, and your destination port, and the connection between these two ports are established, right? And you have a seamless transmission of data from one end to another end without breaking, right? And it is going to be continuously, and it is going to be transmitted via packets, and small packets are being transmitted continuously. That's it. Right? So UDP is something that is an underlying protocol of IP, right? Internet protocol, right? So so the UDP protocol is going to be embedded in your data here, right? So not just here. This is going to be your packet. If this packet had a UDP1, UDP is going to reside on the top layer, okay, of your data packet, okay, and this is going to be having the data of, say, the source port, right? It's going to have your source port and your destination port that you have to connect to make sure the connections are, the data packets are being received continuously. And it also has a checksum here also. So uh, it again computes the checksum of the data, like we computed for the IP. It does the same thing over here. And And this is actually visually visible too. So, for example, when we are having a conference call, we are having a call right now, a video call, and you might have, if you have some kind of an internet issues, you will be missing out a lot of packets. Okay, a lot of packets might be lost when I'm sending it to you, right? And those packets, uh, uh, when you have those packet loss, you just have like you don't hear me at sometimes, or sometimes the visuals goes missing. Yeah. So and so on. So UDP checksum helps you identify the packages that are being corrupt while being transmission to, and they get and they start discarding them once. So in here, in say video calls, this is something that is okay, because you don't need to have a continuous connection, and we can have, if you can't hear me now, you can just ask me, oh, I didn't hear you, can you tell it to me again, and I would repeat it for you, right? And this is something where packet losses, the packets of messages that you're sending, is acceptable. But imagine a situation when you are having a packet loss in the emails that we are sending, right? So now we sent out an email yesterday saying today's class is going to be at 10 o'clock. Okay. And the link to the classroom and everything was in the message. Okay. Just imagine a message you received on the email, all right? And you had some kind of a packet loss, and the packet that you lost had the timing details. I mean, that is going to ruin you, right? Ruin out the email itself, right? You're going to get an email without having a time of when the class starts, and you're going to be completely lost back then. And you have to go to extra steps saying, oh, I don't know when the class is going to start. You have to email back, and we have to email back, and there might be some kind of a problem in that. So there are applications like email and other services where packet loss is not acceptable, right? Where packets are really necessary, right? Now we'll go back to seeing the other problem also, which the next protocol solves. And we just saw that in the previous here, yeah, in this slide. Shashank is receiving packets out of order, right? Now, just imagining a timestamp that is being corrupted by is being split up, and you have a timestamp. Say, if I send you, it's going to be at 10:10 a.m. It's going to be at 10:50 a.m. And instead, due to packet loss, it has something that shows you a time of 50:10, and time does not make sense for you, right? And those packets are out of order, and you need to arrange them together too. All right. So most of these sensitive, packet sensitive applications would require another protocol, which is called as a TCP over IP. Okay, and the TCP over IP protocol helps you solve these problems exactly. Right? So what it does is it makes sure all the packets are received. Okay, it makes sure the packets that you received are put together in the order. Okay, so that you get your email with all your correct time, and you get the entirety of your email, so that you can attend our class today. So so TCP over IP would have that in its address too. So now, if you just look at this here, this thing, this has your IP address, which is going to be followed from the whole IP v4 protocol, but this is going to be your data, right? This whole thing, and it also has a TCP headers. Okay. Now this TCP header is going to have a source port and a destination port, like before. Okay, but it is going to have a sequence number too, right? So now, which is important, right? When you are splitting up an email, you want to receive it in a particular order, and that is what we saw. And it is also going to get an acknowledgement number, all right? And we'll tell you what acknowledgement here is. So, and it is going to have other things that would be there, and at the end, it is going to, send you the data, all right? Okay, so here let's just start off with how this TCP, you know. So once a message is being sent via the TCP over IP, it divides, takes an entire chunk of your message, chops it into pieces, and gives each message, okay, a number, and it goes on giving it a sequence number to know, okay, this email has these many things that we want to look at it. And what it does, okay, is it sends a message. Say, for example, now we are, in the video conference, and Akash is listening to this, right? So the TCP, we are not having a TCP protocol, but when we send out an email, what it is going to do is it is going to send the packet of data. The first packet that it is going to set up, number it as 1, number it, the second packet is 2, and the third packet is 3, and it is going to send it over. Now, once, say, Aka's computer receives those packets, okay, it is going to send an acknowledgement back to me, okay, saying, okay, I received this packet number 1, okay, acknowledgement number. That is going to be your acknowledgement number. It is going to tell you acknowledgement number, this is the packet that I received. And why is this important? Right? While we are sending out emails, we should make sure that all of the packets that we are receiving should be there for us to understand the email, right? So once we get an acknowledgement back, okay, I know that you have received the package, and I can send you the next packet of data. So I can keep transmitting this package of data and receiving acknowledgements. I will resend those packets. Say I send the packet number 2, okay, and which Akash receives, but he sends back the acknowledgement, but the acknowledgement message is being lost, or he does not even receive the packet 2, and I don't receive the acknowledgement of the package that was sent. So what I do is I resend those packet again, and this keeps happening until I've sent the uh, entirety of the message, okay, and I receive acknowledgement for every packet that I've sent. Then I stop, transmitting all of the data. So now these protocol helps us solve these problems very, nicely. So, and also in TCP you have checksums the same way you had in UDP or IP, or IP also carries a checksum. TCP carries its own checksum so that it understands what the message is, and even if you receive a wrong checksum, which is going to be considered as packet loss, you're not going to send an acknowledgement. So again, that I'll be transmitting that packet again. All right. So these are the things that we kind of had a very good, you know, looking at these things of how packets are being sent. So say for us to connect to somebody, like, right. Um, So if you want to connect to somebody, right? Say if we want to connect to some kind of a server, or if you want to connect to some kind of an email service, or messages that we send on Zulip, right? So you need two things. First is your IP address. IP address is where your computers or where the server is stored, right? And you need a port address, right? So here what we are looking at, okay, is your IP address, okay, and for the DuckDuckGo domain, and DuckDuckGo is a search engine similar to your Google, but it is a better search engine because they don't track you, right? So if you want to just visit you can just try typing out this IP address in your browser and mentioning it via the port. Say something like, yes, show you. You can just add this and add a colon 80, which is the port address of the server. And by default, for all of the servers that run on, all of the web servers that run on servers, we'll get to what web server is in the next class. But before that, all of the web servers open up a port called 80, okay, in your computers. And if you just type in this 40.81.94.43 colon 80, you would actually be directed to the DuckDuckGo server, right? So you can contact anybody, right? You can contact me via my IP, and I can contact you via your IPs too. But remembering IP addresses, see, these addresses are going to be difficult, right? Because it's a string of, it's a 32-bit, hash number which you have to keep in mind, and that's not going to work every time. So IP addresses usually take from 0.0.0.0 all the way to somewhere around 255.255.255.25. Okay, and it's the same, and it's the same. Right. So keeping every IP addresses in memory is not going to work, right? So to introduce this, okay, to solve this problem, we are better. We are humans are better in remembering names, right? Uh, we remember the name of Apurva easily. I remember Harivasa's name easily. I even remember Achilles' names easily, right? So remembering names are going to be much more easier for us than to, memorize these IP addresses. So we have what is called as the domain name system, which is actually a service, which maps, okay, your domain name. Say for here your domain name is what we looked it up for this IP address. The domain name is duckduckgo.com, and if you just go search, put this domain name in your web browsers, what it is, the first thing it is going to do is it is going to reach out to the domain name system, which are servers being run by service providers. Okay, and what it does is that it takes this name, looks it up to what IP address is this name connected to, and then sends you back the IP address of that server so that you can get a request to ask you to transfer the files. Say in our case, in the DuckDuckGo, the files you'll be transferring would be the HTML files, right? Because it's going to be a web interface, and you're going to be asking for HTML files. And we'll be looking at how we'll be looking at HTML files and how web servers or this works in the next class in much more deeper. Because but yeah, the domain name system helps you map names such as duckduckgo.coms to IP addresses so that you can remember that. To just give you a vague understanding of how domain structures work, so you have the top level domains such as the .org or the .com, .in, and you have the domain names, the second level domains, which are called which are like something like .duckgo.com or google.com. And each domain name can have a subdomain name of the parent. Like Google has something like drive.google.com, okay, which maps to it might map to an entirely different IP address, and this doc.google.com might redirect to a different IP address on different server, because this is entirely a different application and this is going to be a different application that is being run by Google. Okay. So yeah, so these were the things that I wanted to cover, and this today became a very heavy theoretical class, which was out of our usual standards. We were having a lot of hands-on sessions, but making sure we understand the internet and how messages are being sent and how you are sending packets and how you are receiving packets and what are the protocols that we are using gives us most of the idea of how leading up to how the internet works, and that was something that I felt is necessary for you guys to move on to the next session. So what we are going to be doing is we are going to be having another session which is going to be a hands-on session. Okay. And in that session we're going to be dealing more about how web servers work and how do we write HTML files and how those HTML files get rendered in your browsers and how browsers make requests and basically how the application levels work, right? And much more details of that. So yeah, that is going to be, this is where we are going to take a stop today. And our next class on this, which we are going to continue off, is going to be on Friday. Yeah, on the after tomorrow, where we'll be having a lot of hands-on session, working through web servers and HTML files and a lot more coming through that. All right. So yeah, we are having to finish up, in much smaller time because of all the things that we had today. So what I would suggest is for you guys to go back through things, look up, read more about all of the things that we discussed. Come back to us and ask us doubts of the things that you want to look up. Okay. And yeah. So just to remember, you can also look up your IP addresses using the fconfig.a that I shared before. It would show your IP address as well as your MAC address so that you can have a look up at it, okay, in your terminal, and that will be there. So we are open for questions. So anybody having questions, you can start, picking up the questions, and we can have discussions. Mahesh is typing something. Uh, you didn't give the space. Fconfig space dash a is you have to give a space before the dash a. Mahesh. Try it out. Fconfig is the command. So and dash a is what you're passing as an argument. An R. So it should be separated by a space. Okay. Yeah. I'll just put it out. Pramod is typing something. So you guys can also unmute yourself and talk if you have any questions. We want to try to make this. See, I understand this was a very heavy session today, which okay, can we switch our IP for unlocking websites? Cheeky. That's a nice question, Pramod. Yes, we can, and yes, I'm going to show you that in the next class. Yeah, most of our next class is also going to cover something what is called as VPNs, virtual private networks. And we're going to be talking more about peer-to-peer networks and sharing of files and how files are being shared on the internet and more of the application layers, right? So our next class is going to be more on that. And I will tell you how to do most of those things, prevent the time. Oh, or IP config on CMD or PowerShell works too. Yes. Yes, Shashank. Thank you for that. Yeah, IP config works on people who are working on command prompt on Windows. But yeah, most of the things. So, any more doubts or the things that we talked about today? That's something that you couldn't, wrap your head around, so that I can pick up the questions and help you, get a better understanding of it. Okay. Okay. Thank you, Pramod. Thank you for being present at the sessions. So I guess that's it. For if we have no more questions, we can, schedule then. We can meet up for the next session, and I guess we can. If anybody else wants to stay back and ask questions, you're welcome. Or else, I'll see you in the next session. Tata, guys. Arun, Akhilesh, do you guys have anything to add upon? Yes, yes. Every device has an IP or a MAC address. That's how you connect it, right? So if you don't have an IP address, other routers don't know where to send you the packets to, right? Right. So every device has an IP address. Your IP address is going to be a variable address, okay? And the MAC address is going to be a permanent address. Your MAC address is for your hardware that you're connected to, whereas your IP address, right, is more of an address of, say, your local area connection. Say if you are connected using a Wi-Fi router, your Wi-Fi router is going to have a, what it usually does is it's going to connect it. The router has an IP address, and it is going to the device. So for example, all the devices connected on my router has an IP address which is local, which is going to be 192 point something something something, right? So your IP is going to be the IP of my IP is going to be the IP of my router. And when I connect from my phone's internet, my phone internet connection gets me another IP. So IP is going to be variable depending on the type of the connection that you're using. And but your MAC address are going to be permanent address. It is going to be etched on while your hardware is being programmed. So you're going to have a permanent MAC address for your Ethernet ports or your Wi-Fi devices. So, any more questions, guys? A lot of you are here. Um, yes. So your internet providers do assign your addresses. Nilesh is typing something. So the IP addresses is usually provided by your ISP, internet service providers, and also your the MAC addresses by your manufacturer. Okay, then if you guys have no more doubts, you can drop off so that we can close the session.